Hey everyone, today we're going to solve this problem, that is LeetCode 912, sort an array. It's a medium level problem and it's a very classic problem. It has a good like to dislike ratio. So let's start this problem. So we are given an array of integers nums and we need to sort the array in ascending order and return it. You must solve the problem without using any built-in function in order of n log n time complexity and with the smallest space complexity possible. So obviously this line, okay, if this is a live interview, then there could be a possibility that the interviewer might have said it up front that you shouldn't use any built-in function and solved it under the time complexity that is n log n. But if this is as a follow-up, then you can say that I mean the first approach could be to use something like bubble sort, which is n square, and then they will be asking you to optimize it, and then you can optimize to merge sort or heap sort, which is an n log n algorithm. And then you can go to another algorithm which is not an optimization, but it is a the algorithm is counting sort, and but yeah, it still exists, right? And in certain scenarios it could prove itself to be very fast. So yeah, this is the problem, and let's see. So the first approach, so I'm going to basically, in this problem it has nothing but the sorting, and you can obviously use the built-in sort method as well, but that is given in the question that we should not. And if you treat I'm sorry, and if you treat it like a like an interview question, then at that point we won't be using a built-in method. So there are three algorithms. So the number one is merge sort. So no, let's first discuss count sort. So what is count sort? So for example, we are given this array 5, 2, 3, 1. Let's say 1, 1, 0, -1, -1, 2. Okay, so this is the array. And if we make a counting of the elements that are given to us, what will be the count? So 5, this is present only one time. Then you have 2, this is present 2 times. So you will be like 2. And then 3 is only present one time. 1 is present 1, 2, 3, 3 times. And then you have 0, that is only present one time, and then you have -1, which is present 2 times. Now you are done. Now what you will do is you will have two pointers. So one will be the minimum element, so this will the minimum element, and another pointer will have the maximum element. So you will start, and this is basically the range of the element. So you will start with -1 all the way to 5, and the numbers are 0, 1, 2, 3, 4, and 5. And then at -1 you will look at this map that we have created, the record of frequency. So -1 is occurring 2 times, so in the array you will store -1 2 times. Then at 0, so 0 is only one time, 0. Then at 1, 1 is 3 times, so 1, 1, 1. And then you have 3, that is only one, sorry, now you have 2, and 2 is occurring 2 times, so 2. Then you have 3, 3 is occurring only one time, so you have 3. Now we have 4. 4 is not there, not present in the map or the frequency data structure, so you will not be writing 4 here. And then you have 5. 5 is only one time. So this is the sorted array, as you can see, and this is something that we need to return. Now the time complexity of this algorithm will be, so the time complexity of this algorithm will be n plus of k. So what is n? N is so basically when we are creating this frequency data structure, we need to traverse the array, iterate over each and every element, and n is basically the size of the array. And what is k? K is range of the array element. That means the minimum all the way to minimum and maximum. This is the range. This is the k value, and n value is the size of the array. Now this is not a very good algorithm. There are few reasons for it. So for example, let's say you have -99, and then you have 0, and then you have, let's say, 1, 0, 0, and then you have 1, right? Now the sorting of this array, there are only 3 elements, so the time complexity will be 3 plus of the range. Now range is -99 and 100, so 100 minus of -99, that will be equal to 199, right? 199. So if you are using some algorithm like merge sort or heap sort, then it will be n log n, and n is 3, and log n value of 3 is very negligible, it's very small. So that will give you the time complexity of 3 or something, but it's almost equivalent to 3. But in this case, the time complexity will not be equivalent of 3, it will be 202, which is a bad trade. That is why count sort is not preferred in a lot of cases. And yeah, so this was the thing. Now let's get over this counting sort as well. So we need an ordered map of frequency to have our frequency. Then we need a vector of int answer where the in this vector we will have the sorted nums array and we'll be returning it. Now you need a minimum variable, and that will be minimum element nums dot begin, nums dot end. Similarly, you will have a maximum element. Yes. So after that, you will have int nums. Now we will be storing the frequency. So num frequency will be increased. So for example, if we encounter 5, we will be increasing the value, and in an unordered map, the initialized value of every entry that is not there is 0. So now it will be 1. So now we have to create an element, and we iterate over the range of the elements. So for example, we start with minimum element. An element has to be smaller than or equal to maximum element, and element is incrementing. Now while frequency of this element is decreasing, I will push it into the answer, and at last I will return the answer. Let's see if this will work. Okay, it does work on the default test cases. Okay, it does work. And looking at the time part, I mean, it's okay, it's not that great, but the space part is good. No, the space part is also not good. Okay, anyways, so let's start with, so I think now you can understand why there is some complication. There are some test cases. So for example, in this case where we only have 3 elements and the sorting should take some time equivalent to 3, but in this case it's taking 202, which is not something that we look for in production application. So another approach that we can use is something that is called merge sort. So how does merge sort work? So first of all, the time complexity of merge sort is n log n, and the space complexity is also n. Yes. Now in merge sort, just a second. Yeah, so where will we? Yeah, so space complexity is n log n and space complexity is n. So the time complexity is n log n and space complexity is n. And how does merge sort work? So for example, we have this array, let's say 5 1 1 2 0 0. Okay, 5 1 1 2 0 0. So merge sort will say that we need to divide the array until and unless we cannot divide it any further. And when we are merging the array back, at that merging we will be sorting the array. We will, while merging the array, we will be merged, or no, the best way to put it will be that we will be merging the that we will be, merging the array in such a way that the merged array is sorted. So for example, in this case, you split the array and now the array is split. So 5 1 1 200 200. Then you again split the array, and this is 5 and this is 1 1. You again split the array. Now you have 2 0 0. And this array cannot be split. This is the last part, but this array can be. So 1 and 1. This array cannot be split, but this array can be 0 0. Now when we are merging it back, we will make sure that the array is merged. So 1 and 1 are now merged and they are equal to 1 1. 1 1, right? And 0 0 are merged and they are already sorted, so they will be 0 0. But this time when we are merging them, and right here we will have 3 elements. So now when we are merging it, 5 and 1, which one is smaller? 1 is smaller, so 1 will be here. Then we increment the pointer which is used, and now the pointer is pointing here at this one. 1 and 5, which one is smaller? 1 again. And when the pointer has exceeded, all the remaining elements in the other array pointer will be copied at this array. So now you have 1 1 5. So for example, in this case 2, this is the pointer. 0 is smaller, we increment the pointer. 0 is smaller again, we increment the pointer. Now the pointer is pointing outside and we copy all the remaining elements from the other array, and now we have 2. So now we are done merging this one as well. And when we are merging this array, when we are merging this array 1 and 0, which one is smaller? 0 is smaller, so we increment this one. So we increment this pointer to this part. So 0 is again smaller, so we increment this. Now 2 and 1, which one is smaller? We have 1 that is smaller. So 1 is copied here and the pointer is incremented. 1 and 2, which one is smaller? 1 is smaller. Now pointer is incremented. 5 and 2, which one is smaller? 2 is smaller. In pointer, any of the pointer is out of the bound, the other array elements will be copied to the main array, and now we have 5. So when we are done with this, now you can see we have a sorted array 0 0 1 1 2 5. So now let's see how to solve this problem by merge sort. So I will call a function that is merge sort. Yes, on nums array starting with 0 index, and the last index will be num dot size minus 1, and then I will return the nums array. By the way, this merge sort algorithm is in place, which means that we don't need another new array. I mean, we do need it, but we can sort the numbers inside the nums array only. For the merging part, we do need the, temporary arrays, but they are not returned. We can return the same nums array only. Okay, so now we need two functions for merge sort. So the number one function is almost obviously the merge sort function, which will have nums as an argument. The first index will be equal to low pointer or start, let's say start pointer, and then you will have an end pointer. This is the first function. And when we are using this function, you will realize that we need merging. So for merging, we need a merge function as well. And the merge function will have arguments as the vector, reference, the array that we are merging, the start variable, the end variable, and the mid variable. Now back to the merge sort function. So this function will recursively break the array in two parts, but we need a base condition. The base condition is the start has to be okay, so start has to be smaller than the end variable, but if it is greater than or equal to the end, then it's not acceptable and we'll return. But if it is not, then we will recursively break the array in two halves, and we can do it by saying start, mid, and start and mid. Then I will say merge sort on nums mid plus 1 and end, And now I can merge these arrays nums. So this is start, and then you need end, and then you need mid. Now you will be wondering, how do we get mid here? We need to create a variable mid, and mid will be equal to low plus of high minus of low divide by 2. So this is the merge sort function. Now the merge function, so for merge function this is complicated. So if you like, this is just a heads up, be full attentive for the merge function. So you need pointers, right? Because when I was comparing these elements, so I need a I pointer and I need a j pointer and I also need a k pointer for the main merged array, I pointer for the, this left array, and j pointer for the right array. So I j is equal to 0 and k is equal to start. This is one thing. Now you need size 1. So size 1 basically means the size of the sorry, size of the left array, and that will be equal to mid plus, mid minus of low plus of 1. Now you also need size 2, and that will be equal to high minus of mid. And at last you need vectors. So one is left array, that is of size 1. Then you need a right array, that is of size 2. And I think that's it. Now the first thing, we need to copy elements. So I will say I is equal to 0, I is less than size 1, I plus plus. Left array of I is equal to the main array, and mid plus 1 plus of I. Similarly, we need to copy the elements into the right array. Right array of I is equal to array of, this has to be low plus I, and this has to be mid plus 1 plus I. Now while I is less than size 1 and j is less than size 2, so if left array of I is smaller than right array of j, if this is the case, then we increment the I pointer, because we need smaller element first. We give priority to the smaller element, and that is left of I is the smaller one. So we will increment the I pointer, and k pointer has to be incremented regardless, right? So array of k plus plus is equal to left array of I plus plus. Else if this is not the case, then we'll simply say array of k plus plus is equal to right array of j plus plus. Now, now coming out of this while loop, there is still a possibility that we have remaining elements from the other arrays, maybe right or left array, and we need to solve it. So if I is less than size 1, then array of k plus plus is equal to left array of I plus plus. And while j is less than size 2, array of k plus plus again is equal to right array of j plus plus. So after this part, our array should be merged, and let's see if this will work. Okay, low. We don't have low, we have start. We don't have high, we end. Start. Okay. So we have start here as well, and start. Let's see if this will be submitted. Okay, and it's performing very bad. I don't know why. Although I think if in an interview, if this is the solution like merge sort, then there should be no problem because it's an n log n algorithm and the space complexity is also linear. But anyways, so this was one of the solution, and there's also another solution, and that is heap sort. Now heap sort is a very interesting algorithm. So let's see how this algorithm work. We have heap sort algorithm, and in this, let take this example 51200. Okay, so now I will create a heap of this. So basically heap is not a tree. So first of all, in in a theoretical way, it's not a tree data structure. We kind of represent the child. We make some child relationship or a root relationship between the child and root, and hypothetically said that this is a heap tree, but it is not. I mean, in the coding part it's not a heap tree, but we do represent it via heap tree in the representation part or a hypothesis part. So for example, in this case we have 5, then we have 1, we have this one, then we have, okay, so let's say we are creating a heap now, right? So we have 5. Now we are not just creating a heap, we are creating a max heap, and you will understand the reason why we are creating a max heap. Although you can create a min heap as well, but there would be some exceptions for that. So for example, this is 5. Okay, now we need, so this is 1. So max heap says that the root element has to be greater than all of the children, and this is 1. Okay, it's fine. After 1 we have 2, but in this subtree, there's an issue because this child is greater than its parent, and that should not be the case. So in that part we will be swapping it, and when we have created 2 here, it will be swapped, and this will be now 2, and this will be 1. Now we have 0. Okay, we have 0 here. No, it's not a problem because 2 is greater than 0 and 0 is the child of 2, and the relationship is working fine. And then you have 0 here and it's fine. So when we have created a heap by the process that we call as heapify, now we can go into our array. So we have 5 1 2 0 0. Okay, so this is the array, and I will say that at last I will take the root element because that is the greatest element. So I will paste 5 here and I will swap 0 here. So 0 was here initially and now it is there, and 5 was here and now 5 is here. So we have basically swapped their positions. Now we will run heapify process on this part. So at first we were running heapify on the whole part, but now we are running heapify on the this part only. And now after heapifying this, what will be the so this is basically a way of saying that we don't have 5 now. Okay, so we don't have 5 now, and this is 0, and this 0 is gone. But there is a problem because 0 is smaller than 2 and 1, and this should not be the case. So you will swap 0 with 2, so this will be 0 and this will be 2, and there's again a problem. So 0 has to be smaller than, sorry, greater than 1, but that is not the case here. So this will be 1 and this will be 0. Okay, as you can see, 0 has traveled there, now 0 has traveled there. So 0 will be, so the heapify process will, the heap will look something like this: 2 1 1, and 1 has child 0 and 0. And we will replace, just like this array that we have done, we will swap the greatest element with the last element, and this will be now equal to 0, and we will have 2 here, and this is the array that is sorted, right? And this is something that we again will heapify, and when we will heapify this array, this will look some, so for example, this 0 is gone now. Okay, and at this place we have 0. Now see, there's a problem, right? So 0 1, and it shouldn't be the case. So 0, sorry, 1, and now we have 0 here, and it's fine now. The heap will look something like 1 0 1 and 0. Again we'll do the same thing. 1 is swapped here, and now you have 1 0 here, and yes, the array is stretched to this part, and this array is sorted. Now we have sorted array, 3 elements in the sorted array, and this 0 is gone. And for this part we don't have to do anything. For this part the heap will look something like this: 0 0 and 1. We don't have to, yeah, we do have to do like a lot of things. So 1 has to be the root, right? So 0 will be swapped, and 0 will be here, and we have 1 here, and then we have 0 here. So the heap will look something like this. Again there is a swap, and we will swap it. Okay, do it. Now you have 0 here and 1 here. So this is the sorted part, and these 4 elements are sorted now, and you have this as the heap. You don't have to do anything, it's fine. Swap both of them. This is the array, swap with itself, this is the array, and now you are done. You have all array elements are in a sorted way. So this is the heap sort. So let's write, so first, and now let's talk about the time complexity. For the heapify process, the time complexity is log n. It's log n, but we are doing heapify process on almost all of the elements, you know. So which is why the time complexity will be equal to n log n. Okay, so let's code this up. So just like merge sort, we will have heap sort function, which is going to take heap sort argument, nums argument, and return the nums. And heap sort is also in place actually. Well, you know what, there's a problem actually. I have said that merge sort is in place, and I was wrong. Merge sort is not in place. Quick sort and heap sort, they are in place algorithm. Merge sort is not, because we are using, you know, left, as you can remember, left and right array. So merge sort is not an in place algorithm, and I'm sorry for that. I was just confused with heap sort, I think. But anyway, so let's continue with our code. So just like merge sort, we need two function. So one is heap sort, and it's a void function. It will have vector int nums. Then we also need a heapify function, which is going to take vector int array as the first argument, then the length of the array, and the ith element. So ith element means the root index. Okay, so this heapify function, first of all we need to have nums dot size. Now I will be, first of all I have to heapify it, right? So I will heapify on n by 2 elements, and I has to be greater than equal to 0, and I will give you explanation why we are doing this. And I will say heapify array n and I. So why we are doing this, the reason is, for example, let's say we have okay, so the thing is, for every ith element we have two child. So number one is 2 into I plus 1 as a left child, and 2 into I plus 2 as the right child. Okay, so if I is equal to n by 2, the child are, so you know, if I is equal to n by 2, the child are going to be n by 2 into 2 plus 1. So 2 to cancel, n plus 1, and n plus 1 is out of bound, and n plus 2 is also out of bound. So we don't want to go out of bound. Basically that means that every element after n by 2th index does not have a child, so we don't have to worry about them, because if we can give their root values, the leaves will be the leaves will be, you know, handled by the root values only. So this is the reason why we are doing it just for n by 2 size of the array. Then we need a n minus 1. We need to, you know, as I have said, we need to go from the backward direction of the array and store the largest element on the back, and so on until and unless the whole array is sorted. I has to be greater than equal to 0 and I is decreasing. So now there's a thing that is swap. We need to make a swap as I've told you earlier. The first element and the last element. But after that we need to make sure that the remaining elements have a heap together. So array. Now in this part I have given you in this heapify function. So what are the main things? So for number one is the first argument is the array, right? That is something that is very obvious. The second argument is the size of the heap. Like how many elements do we need to consider to make a heap of the array? So in this part I will say only consider I elements, right? So for example, at first I will only this part I will only I will consider all of the elements, n elements. But in the first iteration of this for loop, I will only consider n minus 1 elements, which means the last element is now swapped, and which means the last element is sorted, and n minus 1 elements has to be heapify. So starting from 0th element, and this I basically means the root index, and obviously I'm going to say that 0 is the root index. Obviously it has to be the root index, right? Because that is what we are making an assumption here. That is why we are using an max heap. That is why we are using a max heap for this purpose, right? So the first is root index is equal to I. Then you have a left child index, and that is equal to 2 into I plus 1. Then you have a right child index, that is equal to 2 into I plus 2. Now if left child index, now sorry, this has to be, left child index has to be less than n, that is one thing, and the array of the value at this left child index. So if it is greater than the array of root index, right, if this is the case, then it's a violation because the root index has to be greater, but in this case the child value is greater, so we don't accept that. We will say root index is equal to the left child index. Okay, and same thing for the right child index, less than n, and array of right child index has to be it. Okay, if it is greater than root index, then root index will be equal to right child index. Now root index, so if root index is not equal to I, that the assumption that we have made that this is a root index, and now after these processes I made an observation that the assumption that we were working on is not correct. In that case we need to make a swap, and I will say array of root index and the array of I needs to be swapped. After that I will recursively call heapify process on the array n elements and root index as it is. Okay, so basically if there is a, so let's say for the first, so this part is going to take care of the first the subtree which is located by the root node, and if there is any other subtrees originated by the root as a child of the root node, then they will be taken care by this recursive heapify function or recursive call. So yeah, let's see if this will work. Okay, it's not performing ideally good, but it's not that as bad as compared to merge sort, so I guess it's all right. Anyway, so this is the problem, and we have learned three algorithms: count sort, merge sort. By the way, merge sort is not in place. Let me just change it. It's not an in place algorithm because we need right and left array. But heap sort is a in place algorithm. As you can see, we don't need live right or left or any other temporary array for the purpose of sorting them. We also have a quicksort algorithm which has an average case of n log n, but the worst case is n square when the arrays are sorted in the reverse direction. But yeah, this is the problem. These are three methods or algorithms that we can use to sort the array. And if you have any question, then you can ask in the comment section. The source code and the problem link will be given to you in the description of this video. And thanks for watching and have a good day.